Hi everyone, Dr. Burns here with our first lesson in Chapter 18, Acid-Base Equilibria and Solubility Equilibria. In this lecture, we are going to start talking about some of that acid-base equilibria. So in our previous chapters, we've talked all about equilibrium, and now what we want to discuss is the factors that can affect our equilibrium. We've touched on this a little bit earlier when we talked about the Le Chatelier's principle, but now we're going to discuss that specifically in terms of acid-base reactions that we've discussed in a previous chapter. So, we have discussed previously that the addition of a reactant or a product can shift a system at equilibrium. That's Le Chatelier's principle. The same applies if a common ion of a product or reactant is added to a system. So let's consider our equilibrium of acetic acid and assume that we start with an acetic acid solution with a concentration of 0.10 molar, which we know from our ICE table here. If we start with 0.1 molar acetic acid, then our initial concentrations of our H plus is 0, as well as the concentration for our acetate ion is 0. As this is a weak acid, we know that our changes in concentration in terms of X are going to be the same, minus X plus X plus X. And then our equilibrium expressions are shown here in our ICE table. We can now solve for those X values and those concentrations at equilibrium. So we know that Ka of acetic acid is 1.8 times 10 to the minus 5. Since that Ka is so small, we can see that X as negligible. And now we can solve for X. So we know that Ka is 1.8 times 10 to the minus 5, and that's equal to our products, which is X times X, or X squared, over the concentration of our reactant, 0.10 molar. So let's grab our calculator so that we can solve for X. So we're going to take that 1.8 times 10 to the minus 5 and multiply it by 0.1. We'll then take the square root of that value to get that X is equal to 0.00134 molar. So that is going to be our concentration of H plus, as well as our concentration of the acetate ion. Now we know from our discussions of acid-base reactions that if we know the H plus concentration at equilibrium, we can use that to find our pH, because pH is a better way of showing acid-base equilibria values. So we can plug in our H plus concentration in order to solve for pH. So we know that pH is going to be negative log of that H plus concentration. And we get the pH of 2.87. So acetic acid is a weak acid, and at equilibrium it has a pH of 2.87. Now, what if we were to disturb that equilibrium? What if we were to add an additional ion, a common ion, to the product or reactant side of this system? So let's think about that. Now consider that we add 0.05 moles or a 0.05 molar solution of sodium acetate, which introduces more acetate ion into the solution. So remember, sodium acetate is just NaCH3COO minus, and there's no minus there, we have a charge balance now. We add the sodium there to charge balance the acetate ion, because we know that sodium has a 1 plus charge and acetate has a 1 minus charge, so they balance each other out. So we use sodium acetate to introduce the acetate ion into this solution. So our ICE table has changed a little bit now. So we have our initial concentration of acetic acid of 0.1 molar. But since now that we're adding 0.05 molar sodium acetate, that's introducing some acetate ion initially into the solution before we've reached equilibrium. So we set up our ice table the same way, noting that our initial concentration of one of our product ions is not 0, but our change row is going to be the same because it's still a weak acid, minus x plus x plus x. And now our equilibrium row is going to be a little different from what we saw before. So we have this 0.1 minus x that we had before. We have the x for the H plus, and now we have that 0.05 plus x as our value for our acetate at equilibrium, our acetate ion at equilibrium. So now we can solve our ice table and solve for x in the same way, because what we're going to see is that our pH is now going to change, because our pH is our value of that acid at equilibrium. And since we're adding a new ion into that equilibrium, we're shifting that equilibrium. If we shift the equilibrium, the pH value is also going to shift. So we can now solve the same way. Ka is still small, so we can still see this minus x as negligible, and we can now see this plus x as negligible as well. So we can plug in our values like we did before. So now we have 1.8 times 10 to the minus 5 is equal to, now our products is x times 0.05, so x times 0.05 divided by that 0.10. We can simplify this top part to be 0.05x, and now we can solve for x. So we get 1.8 times 10 to the minus 5 times 0.1. And now instead of taking the square root of that value, we're going to divide it by 0.05 in order to isolate x. So now we have an x that's equal to 3.6 times 10 to the minus 5. So our x value has changed. Okay, that's a concentration. This is now our new concentration of H+, and we don't have to write it as our new concentration of an acetate ion because we know that it's going to be 0.05. There's going to be very little change, which is why we're able to use our approximation method. So now we can see what happens to the pH. So the pH is going to be the negative log of that 3.6 times 10 to the minus 5. So you get negative log of that answer. And we get that the pH is now 4.44. So that's nearly double of what we saw previously when we didn't have that addition of that ion. So we can see from these two ice tables that the H+ concentration has decreased. Okay, we started in our first one with a concentration of 0.00134 and a pH of 2.87. And now by just introducing a small amount of that acetate ion, we've shifted our equilibrium, which means we've shifted those concentrations. So we saw that our H+ concentration has now decreased and our pH has now increased. So this is still supporting Le Chatelier's principle that we're seeing a change in these equilibrium concentrations, okay, by adding a product or a reactant ion. Okay, now we can quantify that value. How much is it changing? What is it changing by? Okay, we can see that now using our ice tables. So this is called the common ion effect. The addition of a compound containing an ion in common with a dissolved substance causes the equilibrium to shift to the left, or towards the reactant. This is called the common ion effect. Mind you, common ion, this is just one of the ions that we're adding. If we're adding something that is not a common ion, like if we're trying to add acetate and we decide to add sulfate, it's not going to do anything because that's not a common ion. It's not going to affect that specific equilibrium. Could it have its own equilibrium? Sure, but that's going to be a whole different reaction. So it needs to be an ion that is in common with the reaction that you're looking at. So this is observed by a decrease in the concentration of H plus or OH minus ions at equilibrium for a weak acid or a weak base solution, and thus an increase in the pH. So we can see this here just like we saw when we were talking about Le Chatelier's principle in our previous chapters, that if we have our equilibrium here, if we add a product, we are going to drive that equilibrium towards the reactant, thus decreasing the concentrations of our products and increasing the concentration of our reactant. So let's practice just identifying common ions and seeing if they would affect or how they would affect the reaction. So, which of the following compounds, when added to an aqueous solution of HF, hydrofluoric acid, would cause an increase in the pH and which would have no effect on the pH? So the first thing that we want to do is write our equilibrium for HF. HF is going to be one of our weak acids. It's one of our only halogens that's not a strong acid. So we know that HF is in equilibrium with H plus and F minus. So now what we want to do is look at all of these compounds and determine if they have a common ion. We're looking for an H plus or an F minus. Those are our two ions that we're looking for them to have. If they have that common ion, then they would affect the pH because they would affect the H plus concentration. They'd affect that equilibrium. Okay, and it would cause the pH to increase because we're always going to be adding to the product side because the product side is where we have the ions that have to be in common. So first we have NaF. NaF is an ionic compound that can be split up into Na plus and F minus. Okay, so it has an F minus in there. We see that fluoride ion. So based on the fact that it has that fluoride ion, if we added NaF into that solution, it is a common ion. It has a common ion, so this would cause the pH to increase. Next, we have tin fluoride, SnF2. Again, we would have Sn2 plus and 2 F minuses. Okay. We still have that F minus in there, that fluoride ion is still there, which is in common with our reaction. Therefore, this would also see an increase in the pH if we were to add it. Next, we have HCl, hydrochloric acid. If we split that up, we have H plus and Cl minus. Well, there we have an H plus, which corresponds with the H plus, the ion in our reaction. So this would also cause our pH to increase. Okay, now pause your video and try the last three problems or last three examples on your own. Do they have an ion in common with the reaction, and how would that change, how would that affect the pH? Would it increase or have no effect at all? So let's continue. We have sodium ion, Cl minus ion. Those have nothing in common with the H plus or F minus that we have in our equilibrium. So there would be no effect to the pH. Next we have NaOH, sodium hydroxide. So that's a Na plus and an OH minus. We have to remember that the OH is going to stay together. It's not like we're going to have an O and an H plus, okay, that those won't separate. Hydroxide is one of our polyatomic ions, so it's going to stay together as OH minus. So it does not have an ion in common with H plus or F minus. So this would also have no effect. Next up we have water. We've learned a lot about water in this semester so far, and we know that water can break apart into H plus and OH minus in small quantities, but it's still there. So it has an H+, meaning it has an ion in common with our reaction. So this would cause the pH to increase. So let's continue practicing. This problem comes from our ALEKS homework. So you're going to see this after your lecture today when you go to do your ALEKS homework. And it's a two-part problem. And this is the same problem, similar setup of problem that we did at the beginning of our lecture to introduce the common ion effect. So the first part asks us to determine the pH of a 0.30 molar NH3 solution. And the second part wants us to determine the pH of a solution that is, again, 0.3 molar NH3, but with the addition of 0.35 molar NH4Cl. So that's its common ion. So we want to see how the pH is going to change for this base. So the first thing that we want to make sure that we do is have our balanced reaction. We know that it's going to be NH3 plus H2O is in equilibrium with NH4 plus OH minus. Okay, that NH4 plus is now here in our common ion in our second problem. So the next thing that we're going to want to do is set up our ice tables. So for each of these, it's going to be the same setup of ice table with just one change on either end. So I know that we're going to omit water, so I'm just not even going to have it in my ice table just for space purposes. So we're going to have an NH3, an NH4 plus, and the OH minus. Again, I'm omitting water because water is a liquid, does not contribute. And then we have our ice table. So we start off with a concentration of 0.3 molar NH3. And our initial concentrations in this first problem of our ions are 0. Then we know that this is a weak base, so it's going to be minus X, and plus X, leading us to 0.30 minus X, and X. We can see that the Kb value for NH3 is small enough that we can omit this X value. So we can use that to set up our Kb expression and solve for X. Before we do that, let's just write out our ice table for our second problem here. Okay, so it's going to be set up the same way, except we now have to account for the change or the addition of a common ion. So we know that that common ion is going to be the NH4, and it's going to have an initial concentration in the solution of 0.35. So that changes our ice table to be 0.35 plus X, but again, since our Kb is small, this change in X can be omitted. So now we have two ice tables that are similar in setup, but different in the values that they're going to give. Okay, so now we can solve for X. We know our Kb values for both of these. Okay, so what I want you to do is pause your video and solve for X for both of these ice tables. Use that concentration to then solve for pH, remembering that we are given an X value that is OH minus, and OH minus gives us POH, so then we need to use our knowledge of pH and POH to solve for pH. So pause your video and do that now. Okay, let's solve for our OH concentrations. So here we know that Kb is 1.78 times 10 to the minus 5, and that's going to be equal to x squared over 0.30. So we'll take that 1.78, we'll multiply it by 0.3, and then we'll take the square root of that value. And we get an x that is equal to 0.0023108, which we can then use as our OH concentration to solve for POH. So we get POH is going to be equal to the negative log of that value. So our POH is 2.64, meaning our pH is going to be 14 minus our POH. So we'll do 14 minus that value to get a pH of 11.4. So that's our first problem. That's the pH of our first solution. Our second solution is now adding a common ion. So we're going to set up the problem in a similar way. We have 1.78 times 10 to the minus 5 as our KB. But instead of having x squared on the top, we're going to have 0.35 times x divided by that 0.30. So we'll start off the same way, 1.78 times 10 to the minus 5 multiplied by 0.3. And now instead of the square root, we're going to divide by 0.35 to isolate x. So we get that x is equal to 1.53 times 10 to the minus 5. And that's our new OH minus concentration. Therefore, we can solve for POH. We can do negative log of our value and get 4.81, 0.82 with rounding. So our pH is then going to be 14 minus that value. We get 9.18. Now we can see here that our pH value actually decreased. This is because it's a base instead of an acid. When we were first talking about it, we saw it for an acid. This is now a base. The concept still holds because our POH value is what increased, okay? But because POH increased, that means that the pH is then going to decrease because they're relative to each other. So when we're talking about bases, it's the POH that will increase and the OH concentration that will decrease with the common ion effect. So just keep that in mind as you're considering the conceptual side of these things and using that to help check your work when you're doing these problems in your homework. So these solutions where we have these common ions in solution and they're changing our pH and our POH and they're having this effect, we can actually come up with a special name for them. And these are called buffer solutions. So this is when we have a solution that contains a weak acid and its conjugate base. Okay, so a weak acid, WA, let's use a pen, not a highlighter. A weak acid, WA, and its conjugate base. Let's make that HA, that's how we've been talking about weak acids. And its conjugate base, A minus, or again a weak base and its conjugate acid. Okay. So when we have the solution where we have the weak acid and its conjugate base, or the weak base and a conjugate acid, this is referred to as a buffer solution. In a buffer solution, the concentrations of acid and its conjugate base must be comparable. So they must be very close. They must be similar in concentration. The closer those concentrations are to each other of acid and base, the better the buffer solution is going to be because they are in more equal parts of each other. So the only way that we can make these solutions is by mixing the acid and its conjugate base. Now, conjugate base is always going to be an ion. We can't just have, if we're thinking about the lab, if we were to do make a buffer solution in the lab, we don't have ions by themselves. Okay, we can't just have a powdered ion in order to make a solution. We don't have that. we have to instead have a salt. So the conjugate base usually exists as a salt. Meaning it has a common or a counter ion attached to it. So this is usually something like sodium. Sometimes we see chlorine. We saw these in our previous examples. We had Na, CH3OOH. So that was sodium acetate. We also saw NH4. Cl. Okay, so these are ionic compounds. We know these are ionic compounds because they're a metal and a nonmetal, or a metal and a polyatomic ion. Okay, so they really exist as Na plus CH3OOH, NH4, there's a minus there, plus and Cl minus. So when we put them into solution, they exist as those ions. So when we are actually mixing these solutions together, we really only care about the conjugate base ion. But when we're doing problems, you're going to see them presented to you as a salt. So you're going to see a counter ion to account for the fact that we need the ion in solution. So just keep that in mind. So buffer solutions are important to us and the rest of the universe because they resist change in pH upon addition of small amounts of strong acids or bases. Now this is very important for our chemical and biological systems everywhere. Okay, I like to give the example of gastric juices. Okay, the acid that's in our stomach is acidic, but in our body we have a buffer system. Okay, so just because I drink more acid, maybe I drink a soda, okay, that's acidic. It's not like I'm going to burn my throat with that acidic drink as it goes down, or that when I add it to my gastric juices, my already acidic gastric juices, it's going to change my pH so much. If that happened, well then drinking a soda would just kill you. So we need a buffer solution, a buffer present, so that when we add these small amounts of acid or base, okay, it's not going to change the pH so much that it's going to essentially kill us. Okay, so we have these in place so that we can do things like eat food. Okay, and that's also the basis of why you take antacids when you have gastric reflux or anything like that, heartburn. It's because you want to try to get your buffer solutions back into equilibrium using a base to kind of neutralize your acid and stuff. So buffer solutions are very important for all things. We see buffers all the time. Buffers are an example of the common ion effect, which we just discussed, because we're seeing ionization being suppressed by the presence of a common ion. So by introducing that acid and conjugate base pairing, that's the common ion that we are relating to. This also means that, as we saw from our previous examples, that we can neglect X in our ice tables because those Ka's are going to be small, those changes are going to be small, that they're not going to affect those equilibrium concentrations. So, since this is always the case with buffers, the pH of a buffer solution can be calculated using a derived expression or derived equation rather than doing an ice table over and over. So as long as you have a weak acid and its conjugate base in solution, instead of going through and doing the ice table like we saw previously, what we can do instead is use something called the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation says that the pH of our buffer solution, so this is of the buffer, is going to be equal to the pKa plus the log of the conjugate base concentration divided by the weak acid concentration. So sometimes we also see that written as pH is equal to the pKa plus the log of our conjugate base over our weak acid. Now, I personally like writing my Henderson-Hasselbalch in this equation because it reminds me that the conjugate base is only an ion. So it comes from the salt. So remember, we talked about the salts on the previous slide, that the conjugate base is always going to exist as a salt in order to get that ion into solution. This is just the way that my brain sees it, to remember, okay, the acid is whatever is named acid in the problem, and the conjugate base is whatever is the salt in the problem. So we have to keep that in mind. Okay. Now, before we go on, there's a new term in this Henderson-Hasselbalch equation that we haven't seen before. We've seen the use of logs before, we've defined pH before, but our new term is this pKa. So pKa is the negative log of the ionization constant Ka. So just like we have pH, which is the negative log of the H+ concentration, this is now the negative log of the Ka value, leading to pKa. So P, remember that P just means negative log. So it's the negative log of the Ka value. If we were given a pKa and we wanted to find a Ka, we could use the same process that we do with pH to get H+ concentration back out by saying that the Ka is equal to 10 raised to the negative pKa. Now I put this in here because oftentimes tables that have these ionization constants are often given as pKa values so that they can be used in the Henderson-Hasselbalch equation more easily. So if your table is actually given in pKa's, then if you wanted to use that value as a Ka instead, you do have to convert it. Okay, so if you wanted to use the Ka to use in an ice table for a totally different problem, and the table gives it to you as pKa, then you would have to convert it. There are some appendices in some textbooks, or what you find online as well, that give these as pKa's. So you just have to be a little bit wary of that. Just remember to look if the value is given as pKa or Ka, so that you can make sure you're using the value correctly, and convert if you need to. So if you're given Ka and you need a pKa, you're going to use our first equation here. If you're given pKa and you need to find Ka, you're going to use our second equation here. Okay, these conversions are the same thing we saw with pH and pOH. Okay, again, because that P just means negative log, so we can use these to convert between the two. So before we practice more with our Henderson-Hasselbalch equation and really learn how to use that with our buffer solutions, let's just practice converting our pKa's and our Ka's for when we have to do these with these types of problems. So here I have two tables. I either give you a Ka and I want you to find the pKa, or I give you the pKa and I want you to find the Ka. So let's do the first row of each of these tables together, and then you can do the rest of these independently. So in our first table here on the left, we have a Ka of 2.3 times 10 to the minus 9, and we want to find the pKa. So we know from our definition that pKa is equal to the negative log of our Ka value, 2.3 times 10 to the minus 9. So let's grab our calculators and solve for pKa together. So we get negative log of 2.3 times 10 to the minus 9. And we get that the pKa is 8.6. Yes, 8.6, 2 sig figs from our Ka value there. Okay, now let's go and solve for our Ka. We know that Ka is equal to 10 raised to the negative pKa, 4.41. So we'll do 10 raised to the negative 4.41 to get a Ka value of 3.89 times 10 to the minus 5. And again, Kas and pKas, they are all unitless values, so there are no units here. We just have to follow our sig figs, which are given from our values in the table. So pause your video and complete these two tables in your note pack. You do have to have these completed for grading when you submit your note pack. So now that we know about pKa, we can go back to talking about our Henderson-Hasselbalch equation and using that to calculate pH. So the Henderson-Hasselbalch equation is the pH is equal to the pKa plus the log of the conjugate base concentration over the acid concentration. Now this equation relates the pH of the buffer, the ionization constant Ka of the weak acid, as well as the concentration of the weak acid-base conjugate pair. Those words are jumbled up there, concentrations all together. And it's again referred to as the Henderson-Hasselbalch equation, or HH equation, as I sometimes write it out, because that's far too many letters to write out while we're lecturing. So, now, as a reminder, we can only use this equation when we have a conjugate acid-base pair, okay? We have to have that pairing, and the X is small assumption is valid, so our Ka is going to be small. Now, typically, you are going to be using the Henderson-Hasselbalch equation when you're given an acid and a conjugate base. Again, that conjugate base is going to be presented to you as a salt, having that counter ion present with the common ion, so just keep that in mind. Okay, but most of the time you're going to be using Henderson-Hasselbalch because that X is small assumption is most likely valid with a lot of these weak acids. So let's look at how those concentrations of our conjugate base and weak acid are going to compare and how that can tell us about the pH itself. So here we have our Henderson-Hasselbalch equation, and we can relate those concentrations to each other. So if the concentration of the conjugate base and the weak acid are equal to each other, the pH is automatically going to be equal to your pKa. That's because if the A minus concentration and the HA concentration are the same, this ratio is then going to equal 1. Okay? If that equals 1, the log of 1 is 0, and this term essentially goes away. So pKa is equal to the pH. Next we have when the conjugate base concentration is greater than that of the acid concentration, okay, if they're in greater concentration, then the pH is going to be greater than the pKa. And that's because this log portion is going to be a positive value, so you're taking a pKa and adding a positive value to it, okay, and therefore creating a pH that is greater than the pKa itself. You're creating a larger value. And then on the opposite, if the conjugate base concentration is less than that of the concentration of the weak acid, then the pH is going to be less than the pKa for the opposite reasons of what we saw before. This ratio of the log is going to be negative, so you're going to be subtracting a value from your pKa, creating a pH value that is smaller than your pKa. Now, why do I have this up here? Well, because it's always good to check your work when you're doing these types of problems. You know the pKa, you can see what those concentrations are between the weak acid and the conjugate base. Then you can make an assumption, okay, my pH is going to be greater than my pKa, or my pH is going to be less than my pKa. So if it's not holding up to that assumption, the guidelines that we have here, then you did something wrong. So let's look at a problem that uses the Henderson-Hasselbalch equation. So, a solution is prepared that is initially 0.15 molar HNO2, a weak acid with Ka of 4.5 times 10 to the minus 4, and a 0.16 molar NaNO2 solution. We want to calculate the pH of this buffer. So, here we have HNO2 is going to be our weak acid. We know that NaNO2 is going to be our conjugate base because it's an ionic compound that's separated into Na plus and NO2 minus. And we say that this minus is what goes in for the conjugate base. Okay, so we know HNO2 is going to be our weak acid. That's just, it's defined as a weak acid, but also has an H and an A. Okay, so, and then our A minus, that ion, is then the NO2 from that NaNO2 there. So we have all the information we need to plug in to our Henderson-Hasselbalch equation. So let's see, let's first convert our Ka to pKa. So we're given Ka, we want to find pKa. We know pKa is the negative log of the Ka value of 4.5 times 10 to the minus 4. So we do negative log 4.5 times 10 to the minus 4. And we get a pKa of 3.3468. Let's leave a few extra decimal places on there because that's not our final value that we want. So we don't want to take significant figures into account quite yet. So now that we have pKa, we can plug everything in. So we have pH is equal to the pKa 3.3468 plus the log of our ion ratio, which is 0.16, divided by our acid, 0.15. Okay, now when we're doing this in our calculator, we have to remember that this log is of the ratio of those two values. It's not of the log of the top value divided by the bottom value. It is of that ratio itself. So you need to remember how you're plugging this into your calculator to make sure that you're getting the correct mathematical function happening. The biggest mistake that I see in these types of problems is students not typing things into their calculators correctly, usually in how they're putting in their log values. So just remember what we've worked on in the past with these log values. So we have this 3.3468 plus the log of our ratio. I'm going to put that ratio into my parentheses directly, so 0.16 divided by 0.15, close parentheses. Since that ratio is in the parentheses in my calculator, that log is applying to the ratio. If you're unsure of that, or if you have a calculator that doesn't have a screen like this, you can always do that ratio, that 0.16 divided by 0.15, solve that ratio, then do the log of that value, and then take that value and add it to 3.34. So again, you can solve these multiple ways, whichever way makes you feel like you are doing the math correctly so that you don't freak out about the problem. Okay, so just keep that in mind. So our pH of this buffer then comes out to be 3.37 as our pH value. We're going to go down to 2 sig figs to account for that, so 3.4 as our pH overall. So the pH of this buffer, when I mix HNO2 with NaNO2 in almost equal amounts, ends me with a pH of 3.4, which is not too far off from that pKa. So now let's try another one. This is very similar to our previous problems. So what is the pH of a buffer that is 0.5 molar in HN3 and 0.1 molar in NaN3, given that the Ka is 1.9 times 10 to the minus 5? So using your Henderson-Hasselbalch equation and what we did in our previous problem, pause your video and solve this problem independently. Okay, let's solve this problem together. We're going to set it up just like we did before. So before we plug in, let's solve for our Ka, negative log of our Ka value, 1.9 times 10 to the minus 5. So our pKa is going to be 4.7212. Add a few extra decimal places there. So then our pH is going to be equal to that pKa, 4.7212. That's a 2, not a z. And we're going to add to that the log. And this is where we have to remember our concentrations. So this is going to be HA. HN3 is HA. NaN3 is going to be our A minus concentration, okay, because we know that this can be separated to Na plus and N3 minus, okay. So we have 0, let's see, what is it, 1.0 as our A minus concentration, divided by our 0.5 as our HA concentration, and now we just have to plug that in. So we get 4.7212 plus the log, we're going to watch our parentheses of 1.0, divide by 0.5, and we get a pH that is equal to 5.02. Let's see, we have what, 1 sig fig here? So this would be a pH of 5 with 1 sig fig, that 1 sig fig coming from the 0.5 molar. Okay, so we can see from our previous problem and this problem that when our concentrations are pretty close to each other, that pH doesn't vary much from that pKa, okay? But when they're completely different from each other, so when we have 0.5 and 1.0, when they're almost double of each other, that pH is pretty far off from that pKa relative to what we saw before. We're looking for minor changes, like in the hundredths, thousandths decimal places, okay, but now we see it in the tenths decimal places. We're off by 0.3 pH units, okay, so it's a big difference. So this is why we need to have the concentration of our acid and conjugate base be relatively equal to each other so that we have the best buffer possible. For our next problem, we have a similar setup, but now we want to utilize the fact that we have a weak base instead of a weak acid. We can still use the Henderson-Hasselbalch equation and apply it to a weak base conjugate acid pair. Okay, there's multiple ways that you could see this. I believe your textbook goes the route of converting your Kb into Ka and then adjusting from there. I personally find that very confusing for students to figure out when there's another version of the Henderson-Hasselbalch equation that we can use that avoids any type of conversions, okay, from Kb's to Kas. So here's the other version of our Henderson-Hasselbalch equation. Okay, it's set up very similarly. The only thing that we have to remember is that if we're dealing with a base, instead of getting the pH out, we're going to get the pOH. But if we know the pOH, we can easily solve for the pH. We've done that multiple times in multiple different scenarios thus far. So this version of the Henderson-Hasselbalch equation doesn't change anything that you have to do. Okay, we're plugging everything in the same way. We have Kb's because we're working with bases now. Our conversion to pKb instead of pKa is the same as pKa. Okay, and then once you get an answer out, you're going to get the pOH, and then you can just subtract that from 14 to get the pH. Okay, I personally find this approach a lot easier for students to understand because you're not changing anything. It's the same equation. You just have to now go one step further in subtracting from 14 to get pH, which I think we all have a handle on at this point in this chapter. So, what is the pH of a solution made from 0.61 molar NH3, a weak base, and 2.2 molar NH4Cl, given that the Kb is equal to 1.8 times 10 to the minus 5? So our Henderson-Hasselbalch equation is set the same way. We just have to remember now that our notation for our base and conjugate acid notation is going to be different, but we can still use the same concept that we have in the past. So we're looking for a base, okay, it was defined as NH3, and our conjugate acid, our BH plus, is going to be whatever that base is with an extra hydrogen. So remember, this H means an extra hydrogen on there. Well, NH4 has an extra hydrogen on there, and NH4Cl is an ion, or an ionic compound, which we know separates into NH4 plus and Cl minus. So not only do we have the extra H, we also have the plus charge that's needed. So we just got to make sure we can identify what our weak base and conjugate acid is when we're working with this version of the Henderson-Hasselbalch equation. Okay, but we can solve this the same exact way once we've identified that. So we'll solve for pKb now. So pKb is the same setup, negative log of the Kb. So 1.8 times 10 to the minus 5. So our pKb is 4.7447, a couple extra decimal places there since that's not our final number. And we can now plug in for pOH. So pOH is going to be our pKa, that 4.7447, plus the log of our conjugate acid concentration, so that's going to be the NH4Cl concentration, so that 2.2 molar divided by our NH3 concentration of 0.61 molar. So now we can just solve for pOH. So we do 4.7447 plus the log of 2.2 divided by 0.61. And we get a pOH that is equal to 5.30179. Now that's not our final answer, so I'm not going to put it into sig figs. So instead we're going to do that the pH is equal to 14 minus the pOH. So we get 14 minus our pOH to get a pH of 8.7. 2 sig figs from the 2 sig figs in our problem. So that is the pH of our solution when we have NH3 and NH4Cl mixed together. Our final problem that we're going to do comes from your ALEKS homework, and I purposely put this problem in here because it has to do with our rules of logs and how we can cancel logs out when we're doing mathematical functions. So the Henderson-Hasselbalch equation is just that. It's an equation, and every time we've used an equation in the past, we always know that we have all of our variables except for one, and we can solve for one of those variables. The Henderson-Hasselbalch equation is no different from that. However, because we're looking at the ratio of our conjugate acid and our base, or our acid and our conjugate base, okay, we often care more about the ratio between those values rather than the actual values themselves. So this problem is asking us to calculate the ratio of the concentrations of carbonic acid and its conjugate base, bicarbonate, okay, given that we want to have a solution with a pH of 6.62. The Henderson-Hasselbalch equation can be used to determine what that ratio needs to be to get a buffer in a pH range that is of desire. So we can say, well, I want to have a solution, a buffer solution, that has a pH of exactly 7. And if you know what the compound that you're using to make that buffer is, you already know it's pKa. Therefore, all you need to then find is the ratio of those concentrations of the acid and its conjugate base needed to get that desired pH. Okay, so here we want to have a solution with a pH of 6.62, and we want to know the ratio of our acid and our base, our conjugate base. We need to know that ratio of the concentrations in order to get that, make that solution essentially. So we're going to work a little bit backwards. So we know that The pH here is 6.62. Let me get a pen. And then we can solve for our pKa, so we can find our pKa from our weak acids table, which we find to be 6.35 plus the log of our ratio. Instead of writing those out, I'm just going to write A minus concentration over HA concentration. Okay, so now we can simplify. So in order to simplify, we are going to get this log portion on its own because that's where essentially our unknown is. Okay, so we'll take 6.62 and we'll subtract off 6.35 from both sides. So we'll do 6.62 minus 6.35. So we get that 0.27 is equal to the log of the A minus concentration over the HA concentration. So in order to get rid of a log, we have to do 10 raised to the, just like we saw when we calculate pH or pKa from H plus concentrations, or if we're given the pH and the pKa and we want to get back to the H plus concentration or the pKa, we have to reverse that log, that natural, or that log base 10. So in order to do that, we have to do 10 raised to that value. So to get rid of the log here, I'm going to do 10 raised to the 0.27. And here, if you do 10 raised to the log of the A minus HA concentrations, you essentially get out that the HA minus concentration over the HA concentration is equal to 10 raised to the 0.27, whatever that value is, that 1.8621. So in order to cancel out the log, you just do 10 raised to that value, whatever the value is on the other side of the equal sign. That is then the ratio of your conjugate base to your weak acid. Now if we look in this problem, it actually wants the acid on top and the conjugate base on the bottom. So it wants the HA concentration on the top and the A minus concentration on the bottom. So what we have to do is now invert this. So if I wanted to put HA on top and A minus on the bottom, I would just do 1 over 1.8621. We're just inverting it, so doing 1 over that value. So 1 over that value. So that gives us the HA concentration over the A minus concentration is equal to 1 over that 1.86 is 0.5370. And in this we had how many sig figs? Let's see, 3 sig figs? Yeah, I think 3 sig figs there. So we would just get rid of that final 0 there. And that is the ratio of the concentrations that we would need to get a pH solution or buffer with a pH of 6.62. So that is the ratio of those concentrations that we need. Again, I bring about this problem from our Alex homework because you do have a few in there that ask you to find the ratio of these concentrations rather than the specific concentration or the pH, so just using the Henderson-Hasselbalch equation the same way, just solving for a different unknown value.